If you know that A and B and C are greater than 0, or I mean, we could have, how can I say this? Greater than or equal to 0, but I have A not equal to 0, okay? I mean, that's what I want to say. If you have those conditions, actually I need that, I have to rule out the case that B and C are both 0. How to say this? See, the thing is, if I have y prime prime equal to 0, right? That gives me y is equal to c1 plus c2t. And that solution diverges. As t goes to infinity, that gets really, really big, right? But if I can rule that out, ruling this out, so I can, if I rule that out, basically I can say ABC greater than 0 and B, how can I say this? BC not equal to 0? No, that's too greedy. I don't know, I'm having trouble with case-wise logic at the moment. B and C both not 0. If you do all that, right, you're left with, if you think about it, either a quadratic that has a pure imaginary solution, or a complex solution, or distinct real solutions. And when you get into the details here, you'll find out that the exponentials have negative arguments. The fact that the coefficients are positive, it forces actually the exponential. I mean, think about it. Lambda squared plus 6 lambda plus 5. What happens? You get lambda plus 5 times lambda plus 1, right? The fact that these coefficients are positive forces the zeros to be negative. And so the solutions then go to 0. The homogeneous solution will go to 0. And in the case that you have the complex solution, the real part of the complex solution gives you like an e to the minus something t multiplying sines and cosines. That piece also goes to 0. The worst thing you can have is just like sines and cosines, like this. And even that doesn't go to infinity, it's bounded, right? This is usually a homework problem I assign you guys. I just didn't assign it because I wanted to talk to you about it in class instead. Because every time I assign this problem, you guys get really confused. So I figured I'd confuse you in person instead. And long story short, for real physical problems, the homogeneous solution to a second-order differential equation, either coming from an RLC circuit or from the spring mass problem, the homogeneous solution goes to 0, or it's bounded in this hypothetical simple harmonic oscillator case. And that's why we say the particular solution is the so-called steady-state solution. It's the piece of the solution that endures after the time has gone on for a while. It's how the system ultimately behaves for large times. It's actually what you're most interested in for applications. Because the initial conditions, the C1 and C2, unless we're in this very, very special case, they're really transient. They just go to 0 after a little bit. So the particular solution is the interesting case, is really what I'm getting at. All right, I was going to give you guys a laundry list of annihilators. Let me do that. We still have some time. Yay. Oh, that will take me at least a half hour to solve. But we'll work it out. Okay? This is what's known as resonance more generally. It's not this case of unboundedness, it's the case of like maximizing the response of the system by choosing an appropriate matching frequency. There may or may not exist such a frequency actually. I know because I have at times assigned this as homework and asked them to find the maximizing frequency only to get back, there is no maximizing frequency. At which point I was like, oh, oops, I didn't know that could happen. Yay, I guess I learned something. It was not a bad student either, like it was a very good student, so I knew that something was wrong with me. Let's see here. And of course, when I say bad student, I'm not talking about them as a person. I'm talking about them mathematically. You know, I'm not Iridos either. I don't talk about people like they're dead after they stop doing math. Not my view.
When there's no resonating frequency, so like how they try to design buildings and stuff like that.
Oh right, yeah, you.
Analogy there, or am I just
I mean, the problem of resonance is a big problem for engineering, right? Trying to avoid it, especially resonance with like seismic waves. You want to minimize that, right? Okay, so here's some annihilating. Let's do some annihilation. All right, so function A. So here we're looking at the problem L of y equals to g, and we're trying to make A times L y, because we know if we can do that, I mean, again, our motivation is that it helps us understand undetermined coefficients. Anyway, so here it is. Start out small, 1. Here's how I look at that. Lambda equals to 0 gives me 1 as a solution. You're like, you have a really weird way of looking at 1. I know, I do, but that's why I put D here. This might be helpful to you as I say something like x e to the x. Well, you see now what I have is I've got lambda equals to 1 2 times, right? Which is coming from d minus 1 squared, y equals to 0, right? So that's why I would put d minus 1 squared here as an annihilator for that guy. I'm working the differential equation backwards, right? Rather than solving the problem, I'm asking myself the question, I've got a function. For what differential equation is it a solution? It's the inverse question, right? So like, how about cosine of 3x times e to the x? Well, see guys, this is coming from lambda is 1 plus or minus 3i, right? And from our discussion in previous classes, I know that's coming from something like d minus 1 quantity squared plus 9, right? So like that, acting on y equal to 0, that gives me an e to the x cosine 3x as a solution. Right. So my annihilator, d minus 1 squared plus 9. Of course, you could FOIL that out and so forth, right? AKA d squared minus 2d plus 8 plus 10. I can't do math. All right. All right, guys. What if I had e to the 3x plus x squared? Can I take off the training wheels a little bit here? So I do d minus 3 to get the e to the 3x. And how do I get x squared? How do I annihilate x squared? Yeah, exactly. See, not hard. You can do it. And so, yeah. And by the way, if I added plus x plus 7, it wouldn't change anything, right? Yep. Right, like, for example, if I have x cosine x plus sine x, I can use what? Let me make this a little bit snazzier. Let me make that a 3x. Ooh. I'll show you over here. So this, of course, is coming from lambda equals to plus or minus 3i 2 times, right? Which is d squared plus 9 squared, right? That's where that would come from. So I do d squared plus 9 squared. That automatically gets the sign just as well as it gets the x cosine. What else could I add to this without changing the annihilator? 13 cosine of 3x, right? And then I could also stick in plus 144,352 x sine 3x. I mean, whatever. Any stupid combinations of sines and cosines or multiplication by x's are all covered by that. This thing all sends them to 0. Right? None of them survive. So it's very violent. Do you guys have any other examples that you'd like to pick out? I mean, you can mix and match these. If I do something like x e to the x plus 1 plus e to the x cosine 3x, then what I do is I just multiply the ones we had before. Yeah. If I had x to a negative power, 1 over x, for example. I guess I would build a shrine in his honor. I would lift him up. I would exalt him, for he would be the savior of this function kind. I mean, that would put a stop to our annihilating ways. For 1 over x is not a solution to a constant coefficient differential equation. And there you go. That's a great question to end with. This we can't do. We can't annihilate that. And that's because the method of annihilators and correspondingly the method of undetermined coefficients has limits. Right? We can only tackle forcing functions which are built from sums or products of the constant coefficient problem. 1 over x belongs to a different differential equation. I could annihilate that with an operator built from the Cauchy, corresponding to the Cauchy-Euler problem. But that's not standard fare in here. So anyway, next time, we'll eventually get back to this. This is later. I felt like I should give a shout out to resonance since we went through the trouble of working out that 1/2 t sine t, which is it's a substantial calculation, right? Anyway, so next time, we'll cover what's known as variation of parameters. This is a general method which will give us a way to, if you're given a fundamental solution set for a nth order linear differential equation, variation of parameters in general gives you a method to construct the particular solution. Now, it may or may not be tenable to actually find an explicit closed form answer for it because the integrations which are involved may be undoable, but at least it gives you an integral solution at a minimum. So, thanks guys. Sorry for my coughing.
So mission 3 is due on Thursday and mission 4 is due next Tuesday?
Right, yeah.